Nice poster. Table tennis. What's this about?
Yeah, we're trying to get the 3D ball trajectory and the initial spin of a table tennis ball in real broadcasting videos. And we're trying to do that to get some cool gameplay statistics, make some nice visualizations like those you maybe have seen in tennis. And we also want to help the players with training and analyzing their gameplay style.
So this is 3D. What kind of data do you have? Do you have motion capture?
No, in fact, I don't have any 3D data at all.
Oh.
And no one really does. You could capture some data in the lab, but those trajectories would be very different from the trajectories from professional players. And also the visuals would be very different.
So if you can't measure it, how do you solve it then?
Instead of using real 3D data, I generate some synthetic trajectories using a physics engine. So from that, get 3D ground truth trajectories. But the cool thing is also that I get ground truth spin. And this spin is actually the hardest to get because you can't see it visually. But it has a very strong effect on the trajectory due to the Magnus effect. And using this ground truth, our network learns to infer the spin from the observed trajectory. So we use the synthetic ground truth to train our model.
But if you train it on synthetic data, won't that be problems if you want to generalize to real videos? Usually this fails, right?
Actually, that's no problem at all. And that's because we use a two-stage pipeline that you can see here. We have a front end that's basically 2D detectors to detect the ball position and some table key point positions, as you can see here. And we train those detectors on real data. We created a data set called TTHQ. And in fact, it's very easy to annotate 2D data. You just click it in the images. So we train our models. We get this 2D trajectory and some table key points. And we use only those points as input to our backend. The backend lifts the 2D data into the third dimension. You can see that here. And the cool thing is that it does not have any visual information at all. It just uses those 2D coordinates. And since it doesn't have any visual information, there's not really a synthetic to real gap. And we can get zero-shot generalization.
So what about in the wild data? This will have an impact on detection performance, right? What about varying frame rates, frame drops, or color differences?
That's no problem because our 2D detectors are trained on this TTHQ dataset that we created. And that already includes varying angles, different scenes, different colors, and also different frame rates. We also implemented some cross-architectural filtering techniques so we can get rid of nearly all false positive detections. And we adjust our backend to deal with that by introducing an exact timestamp positional encoding as a rotary positional encoding. And this also allows us to incorporate varying frame rates very naturally. And also frame drops are no problem at all anymore.
So you're saying that this is an end-to-end application for in the wild data that works without having seen 3D ground truth data. That sounds cool.
Yeah, thank you. And that's only possible because we use the real data where we need it, because visual information is present. And if the trajectory is only governed by physics, we can use the synthetic data.
So can I look at some example videos, or do you provide any code?
Of course, just look at this QR code and you will find some example videos and you can try out our code yourself.
Nice, thanks. Good work and see you around.
Thank you.